Hi everybody, it's Katie again from Alveston Park Friends, and we are back for day number 7 of our star party. This is Friday, Day of Venus. Huge apologies for being a couple of minutes late. Just having a few technical issues. I wanted to make sure that those live streams were okay. Just a note on that. We've been having a few little things that I've had to tweak. I have tried to do the constellation craft, the constellation pinwheel. Thank you to Theo, who did some spell checking and realized that I'd put it up as consolation pinwheel. That wasn't great. Thank you. That was changed, but then I realized that the whole of Wednesday's Mercury Day had been uploaded onto that. So I'll get the other little video. It's available here on Crowdcast, but I'll get that over to YouTube sometime tomorrow, hopefully. So what we have to for you today we've got Venus. So we'll be talking about the hottest planet in the solar system. Then you've got more of me and little romp really through several billion years of a star's life in stardust. What have we got? Hi everybody. I like that, Star Bear, thank you. Welcome to the star party where even the sky is not the limit. Brilliant. Is the Mariner 10 image of Venus going to be on here? I think so, yes. Depends which one you mean, but they're all out there too. Starbear says, great discussion last night. People, I don't know about you, but I've started photo stacking my selfies to smooth out my snout. Okay, I could try that, I suppose. Right. I'm just going to have to find the file that I need, and then I'll start sharing it with you. I've been having a massive play around. Probably not a good idea at this point, but I've been doing it anyway. And yeah, Judy, if you're there, I'm going to do my best to use your greenhouse picture, but I'll need to set that up a little bit as I go along. The other issues kind of got in the way a little bit, and well, hopefully that will work. Thank you to Judy, who brilliantly obliged when I asked her for a photograph of her greenhouse today. I'm still not getting this, so oh, 'tis the day of technical problems. They were bound to come up at some point, and it looks like they're doing it now. Slideshow. Right, I'm just going to try opening that again, and hopefully hopefully we'll be getting this on the road very, very soon. Oh, there we go. Okay. I'm sorry, people. I'm not a multitasker. This Friday is the day of multitasking, it seems. But let's get on with this and let's see if this finally works. So I'm going to try and share. Click on that. There we go. Can you see Friday, Day of Venus? Is it up there? It looks like it is. Ah, brilliant. Cool. So I'm going to take you to, blank slide. There we go. Here's Venus in the park. Okay, we promised to bring some of Alveston Park here to you because we're certainly not suggesting that you should go out there and have a look. I love the contrast here. This is Venus in the snow. Venus is, of course, the hottest planet in the solar system. I say, of course, it's not entirely obvious that it should be. Venus has, because it's not the closest planet to the sun. Mercury is the closest planet to the sun. The secrets of Venus I will let you into very, very soon. But first, Friday. Friday has been associated with Venus for many, many thousands of years. Okay, dates back about 2,500 years to the Babylonians, and that was taken on board by the Romans, whose goddess Venus, she was a goddess of love, born from a sea foam. There you go. Now, if you're wondering about Friday not sounding very Venus Day like Saturday is a little bit more like Saturn Day. Well, that is because we have had a lot of Norse influence. And Friday is actually named after Freya, again, goddess of love and domesticity. And there's a story that I would like to tell you that also has a little bit of Russian influence as well. So this goes back to Thor, our thunder god with the giant hammer, who's associated with Jupiter that we saw yesterday. Anthony says, not a place you want to visit. No, Venus is not nice. So Thor, so this story goes, was fishing. And he was feeling sleepy. He heard somebody singing and he fell asleep. And he woke up to this incredibly horrible sound. And he went off to see what this was. And he realized it was a cat called Bayan. And he was trying to sing to two little kittens, Beigel and Tregel. And Thor asked him about the kittens and the cat Bayan. He said, yes, he had met a very attractive female. They'd had kittens together, but now he'd run off and left him as a single father. What was he to do? Now, Thor had an idea. So he took the cats to, yeah, you've guessed it, he took them to Freya to look after, leaving Bayan to fly off as a bird, quite literally. He was free to go. Freya probably thought it would be quite nice if she were asked. I think it would be quite nice if she were asked. But she took on the kittens, and when they grew up, she trained them as chariot pullers. So she had a very, very cool chariot pulled by her two cats across the sky. So really cool thing with the chariot, Freya. But yeah, perhaps we should remind Thor to ask next time. But it did remind me of the animals that have been in space. We've had, you would have thought, as we being humans and wanting to be pioneering, we want to explore, to discover, and we're a little bit competitive. We want to be the first. You would have thought we would have wanted to be the first in space out of the animal kingdom. I think, and one of the astronomers can feel free to correct me on this, we gave that honor to fruit flies. Okay, so hats off to the fruit flies who paved the way. After that, of course, we had a whole series of other creatures go into space before us. Probably viruses got into space all on their own without help from us, but you'll have to forgive me if I don't want to salute a virus at the moment. But following on from the fruit flies, we had all sorts of things, nematode worms. We also had the dogs. The Soviets like to train up dogs, so we had Laika, and Laika was followed by Belka and Strelka. They came down to Earth. One of them had puppies. One of those puppies was actually given to JFK as a gift. I'm not sure whether anybody asked him if that's what he wanted, but that's what he got. Yeah, JFK, I'm sure you realize a little bit about how Freya felt there. But the Americans, of course, they like to train up monkeys. They thought they were trainable, but those cats of Freya's chariot, they reminded me of the French space program. They decided that they would train some cats to go into space. I'm not sure how they managed to train a cat. I did try to train my cats when I was younger. I had no success whatsoever. They were much better at training me than I was training them. However, one of these cats, her name was Felicette. She did go into space. It was a 15-minute journey, but she paved the way up there into space. 1963, she came back down, parachuted safely to Earth. And that's such a nice little story if I end it there, which I will. Onto the planet here. This is, I think this is the Mariner picture. This is the same picture that has then been enhanced. It's not the one you were thinking of. Apologies. But this is just an example of an image that was taken, and then the information that was gathered in that image was then drawn out decades later, and this is what we've got. It's a cloudy world. Those clouds are not nice clouds. They're full of sulfuric acid, they're full of thunder and lightning, and they trap in the sun's heat. And what we have on Venus is a runaway greenhouse effect. The sulfuric acid will, of course, start to dissolve any spacecraft that goes through into those clouds. It is hot enough to melt lead on the surface of Venus. And to map the surface, the Soviets did actually manage to get a spacecraft down on the surface, and it lasted for a couple of hours before it stopped working. But the conditions are so hard. There's currently a number of countries that are looking into things that they can do to protect a spacecraft so we can go back down there and gain more information. But for now, we have to borrow technology from animals. And I loved our discussion yesterday about different animals and the way that they could use the magnetic fields to find their ways around. And we have to borrow some animal technology for this as well. What we do is borrow an idea from bats. Now, bats use echolocations. They send out signals that go out, they bounce off things, and they come back. And the longer they take to come back, the further they are away. And this is how bats can fly around. I was absolutely taken aback when we had a bat walk in Alveston Park one year We've had several bat walks. They are absolutely amazing. If we ever get them going again, do come along. But I was taken aback when I was told by the leader of the walk that bats would actually be as loud as a jumbo jet taking off right next to you. You know what? I thought, no way. No way. So I looked it up and I discovered that it wasn't quite right. That was nowhere near loud enough. The best image that I can get to convey the loudness of bats is, imagine you standing on an aircraft carrier in some sort of Top Gun theme, with jets taking off all around you, all at the same time, buzzing over your head. You're probably getting close to how it sounds to bats. So when you take a lovely twilight, peaceful walk through woodlands, when you're next to a body of water, a river or a lake, and you see a bat, you can be glad actually that we can't hear sounds that high, and we get to do that peaceful walking. But back to Venus, again, just like bats, we send signals down through those clouds, through those thick clouds. They bounce up. The quicker they bounce up, the less they've traveled. So we can actually map the surface, and you can get pictures like this by doing that. You can see that we've got mountain formations here, lovely topography. If you're wondering about the colors on here, now you're bouncing radar signals off the surface here, but the colors are taken from information taken from the Venera missions by the Soviets as well. So they've tried to do the colors that way. Anthony's lovely, thank you. Volcanoes, the bright area in the foreground. Yeah, these are lava flows. Thank you for that. You can see that you've got volcanic activity here, or evidence of volcanic activity here. It's really quite incredible. I like this picture too. Absolutely stunning pictures here. You can also use color to contrast and see different landforms and things like that. So this is a obviously false color image of Venus that is useful to us. But now, I'm going to see if I can get one of these pictures out for you. Starbear says, are there craters? That's a really good question. I should imagine not very many, because there will be craters. You can see them. Okay, you can see some. I say these are craters. Down here are craters. But that thick atmosphere is going to burn up a lot of rocks before they get to the surface. I'd expect far fewer craters on Venus than on Earth. Kay says, what do the different colours depict on the Venus image? Those are different heights of land. So I think these whitey reddy parts are the highest parts, and the bluey purple ones are the lower parts there. I shall try and get this greenhouse up. Let me see what I can do. You just bear with me one moment. You know what? I'm going to be brave here. I'm going to try and share something else with you. I'm going to try and draw. And no. Today is a day of technical issues. How about I just tell you? What Venus has is a runaway greenhouse effect. Now, if you can imagine a greenhouse, I'm so sorry, Judy, for not being able to use this. If you can imagine a greenhouse, if you go into a greenhouse at any time of the year, you'll find it's a little bit warmer inside than out. Now, greenhouses tend to have glass tops, glass roofs, and that lets sunlight in. Now, if you've ever worn something black on a sunny day, you'll know that it gets really, really hot very quickly, far more so than if you are wearing something white. White things, they reflect light, all the colours of the light. Black things, they absorb all the colours of the light. And what they do is they re-radiate that energy at longer wavelengths. So they'll re-radiate it in the infrared, which is heat. Now, light can get through your greenhouse window. Infrared can't really get back out. Heat can get out in other ways, but it can't really get back out. So it bounces off the greenhouse roof and then back down. And this is what warms a greenhouse up. The light will come through the windows. It will be absorbed by the stuff around it. The soil in particular is dark, it's black. It'll absorb a lot of that energy and it will get re-radiated out. Now, we are putting into the atmosphere a layer that does much the same thing as the glass panes at the top of a greenhouse. We're putting in a layer of carbon dioxide. And what will happen is that the carbon dioxide will let the sunlight through, the sun's energy through, and it will bounce off things, but it won't be able to come out. It will go up and down and be trapped. Now, this causes a lot of feedback effects. First of all, here on Earth, we're finding our ice caps are melting. And ice is white, it's really reflective. That will bounce back a lot more of the sun's energy than, say, melted water in the oceans, which absorbs more energy, which will heat the oceans up. It will make them expand on its own. Okay, you don't have to add any ice to that water, just heating it up will expand it. You've got warmer water, and that's going to melt more ice, and you've got what you'd call a feedback loop. Okay, what you've got in Venus is a complete runaway greenhouse effect. That carbon dioxide is trapping in the sun's energy and it can't get, it's absorbed, it can't get out, and that's why it is hot enough to melt lead. Okay. Well, I'm going to go on to Stardust now. I've still got an errand there. Okay. We might as well start with this picture here. I'll have a look at some of the things that have been said just before I go on. We've got a good conversation about water there. If you want to know about water, just read the chat at the sides. If any of you got any specific questions, feel free to use the question section at the bottom. I will do my best, okay? But I think we'll move on now from Venus and the heat of Venus to go to somewhere even hotter, and that's the stars themselves. This is a lovely constellation that you can see at the moment. This is Orion the Hunter. You'll notice I look for a rectangle of 4 stars. I think of these as his armpits, okay? These I think of as his feet, actually, but you can see that they're kind of where his knees are in this image. That's fine. The Orion belt across his middle. 3 stars. They're really lovely. If you find this pattern in the night sky, his shield is a little bit hard to see, as his club here. But this belt is really easy. By the way, if you follow Orion's belt downwards, you come to the brightest star in the night sky, Sirius. If you follow Orion's belt upwards, and we'll be going there later, you come up to another bright red star, and that's Aldebaran, and that marks the eye of Taurus the bull. We'll meet Taurus a little bit later on. But what I love about this is if you look just below Orion's belt, you can see his sword. And it's got 3 points of light. The middle point of light isn't a star at all. It is the Orion Nebula. And this is where we'll really start our story of the life cycle of stars, because this is a place where stars are being formed right now. Now, this is a gorgeous, gorgeous photo. And you can see that you've got these clouds of dust and gas. So I want to take you back now to just looking at that, I'll take you back to what we think was the beginning of the sun and the rest of the solar system. And that was a long time ago. We need to go back in time about 5 billion years. And there would have been a nebula, maybe a little similar to this, dust and gas, and it would have cooled. It's very important that it's cooled, because that means gravity can pull things towards it. Okay, we all know about gravity. If we pick something up, I've got a pen here. You know that if you drop it, it's going to be pulled down by gravity. Okay, the thing that is not really thought about so much is the idea that this pen is also pulling the Earth up towards it. In fact, anything that has mass, that means it can be measured in kilograms, it can be, has gravity. And there's a lovely Derby link to this. There is somebody who is buried in Derby Cathedral. His name was Henry Cavendish. Now, Henry Cavendish at the time was the richest man in England. This meant he could pretty much do whatever he wanted. He's kind of in a position that Elon Musk is now. He's got a lot of money. He can do whatever he likes. And what Henry Cavendish liked to do was science. And he already knew, this was about 1797, he already knew that everything that had mass had gravity. This comes from Newton. And he used this idea to set up an experiment. He had to make this mahogany box that housed metal spheres. He had 2 metal spheres that were allowed to swing, twist backwards and forwards. He used that to work out what's now known as the gravitational constant. Amazingly, 1798, he got a value for the gravitational constant that is within 1% of today's values. It was 100 years after he completed the experiment that anyone was even able to replicate it. It was so carefully done and thought out. But this earned Henry Cavendish the nickname the man who weighed the earth, from the gravitational constant that effectively gave him the density. People already knew how big the earth was and volume, and so it was a simple equation to work out the mass. So we know that things with mass, even tiny specks of dust in space, have mass. And as long as the energy is low enough, they're not flitting around at high speeds, the gravity can take over and pull these things together. And these things get bigger and bigger and bigger. If any of you have been out there making snowballs in the snow that fell earlier this week, this is a little bit like how objects would form in these dust clouds. You'll notice that as your snowball gets bigger and bigger, if you ever get to the stage where you can roll it around in true kind of snowman creation style, you'll notice the bigger it gets, the more stuff it pulls onto it, the easier it is to pull stuff onto it. I did try making a little video of the snowball collection with this in mind, but it just wasn't sticking together. It wasn't snowman snow, at least where we were. So you'll just have to imagine that for a while. Now, eventually, these things will get bigger and bigger, and effectively anything that's going towards the center of gravity is falling, okay? And it will get hotter. It will get hotter and hotter until eventually the temperatures and the pressures in the center are so great that hydrogen atoms can get squeezed together to make helium. A lot of this gas cloud here will be hydrogen and helium. And that point at which those hydrogen atoms get fused together into helium atoms, that's nuclear fusion. That releases energy. That's when a star starts to shine. And that's what you can see happening here in the Orion Nebula. So these are very young stars, and I should imagine more forming there now as we speak. Let's move on a little bit. Before we move on, the planets, by the way, not all of this stuff was hydrogen and helium. There were other bits, and some of it was material that came together in this swirling mass of stuff, and that formed the planets. They formed in much the same way as the star, but they just didn't get big enough to shine. Sometimes you get two stars forming in a system. That's a binary star system. They're very common. In fact, I think we're a little bit unusual here in only having one star, but the planets just didn't get big enough for that nuclear fusion to get play through there. Thanks, Brian. He says there's at least 4 in that center where the white bit is. I presume you mean here, Brian. Okay, where that is. That's incredible. So the planets, Earth has an age of about 4.5 billion years. That's 4,500 million years. Absolutely incredible. And once a star is born, here's the sun, it will shine. And it will shine, it does change a little, but it will shine for a length of time that depends on how big it is to start with. The biggest stars will have the shortest lives. Some of them will only live for maybe 10 million years or so only. Our sun, that's been around for 5 billion years, and it will carry on shining pretty much as it is for another 5 billion years. 5,000 million years. It is an incredible amount of time. Think about that. Do not worry about this happening tomorrow, please. Some people have in the past when I've said this. So what will happen in 5 billion years? Well, to understand that, we've got to understand how stars keep their shape. There's nuclear explosions going on in here that are trying to rip the star apart, but they are balanced by the force of gravity pulling the star stuff inwards. At the moment, the sun is mostly burning hydrogen gas. It's changing it to helium. There will come a time when it runs out of that hydrogen and it starts to fuse helium. Now this will produce bigger explosions and the sun will expand. This will be its red giant phase. Now, as I'm saying this, remember the distance between us and the sun at the moment is roughly 93 million miles. This star, if it were a hollow ball, you could fill it with 1.3 million Earths. So it is already absolutely enormous. Sorry, I'm just laughing at Starbear. Should I cancel the milk? Probably, yeah. But what will happen is it will start to expand, puff off its outer layers, start to expand, and it will engulf Mercury, planet we explored on Wednesday. That will end up inside the sun. It will carry on expanding. It will go and eat up Venus. It will probably swallow up Earth as well. I think your milkman or woman will have other things to worry about by that time, Starbear. And what will happen then is the explosions in the center will die down. That will allow the gravity to take over, and the core will collapse, and it will fuse together all sorts of other things. And in the case of the sun, it will become a white dwarf star. Now, this is an artist's impression of a white dwarf star, a white dwarf. And you've got all of this stuff from the outer layers. Stars will puff off about 50% of their outer layers. It has rings because all of the time in space and things are spinning round and round and round. That's why the solar system is effectively a pretty flat ring. It comes from that original nebula spinning as the stuff came together. And actually, as a star collapses, it will spin faster and faster. I realized last night that Dancing on Ice had started, so I watched the first one last night as a little chill out. But if you think of ice skaters, if they spin, they start off with their arms stretched right out. And then they'll bring their arms inwards and they will spin faster and faster and faster. It's effectively what stars do. They stretch their arms wide when they're in the red giant phase, And then as the star collapses inwards, they spin faster and faster and faster. Okay. And this is one of the effects of that. Things end up as a kind of disc shape there. Now, one of my favorite white dwarf stars it's got a catchy name. It's called BPM 37093. Yes, I did have to write that down. But I like its nickname. It's got a Beatles-inspired nickname. I'll give you a few moments if anybody wants to guess the Beatles-inspired nickname to a white dwarf star. If any of you have been to our star parties before, I have had this as a quiz question on more than one occasion. So I'm testing you now. I'll carry on talking about what will happen and you might get it. We've modelled these and we think what the sun will end up as will get us when that star collapses, when the sun collapses. You'll fuse together heavier things than helium and you'll get about as far as carbon, and a particular sort of carbon, and that will be diamond. Anthony's got it. Lucy is the name of that star that I mentioned. They call it Lucy, from Lucy in the Sky with Diamonds. Now, I think it's quite incredible. If anybody, well, I'm sure you all know the nursery rhyme, Twinkle, Twinkle, Little Star. Well, they say like a diamond in the sky. That song predicted what the sun will end up as. That's absolutely incredible. My childhood song to a real diamond in the sky. So that's what will happen to the sun. Let's finish with what happens when a star much more massive than the sun ends its life. By the way, this clearly isn't the end of the star's life. White dwarf stars will just shine for a bit, for a very long time, and slowly over billions of years fade away. They just kind of fizzle out, really. Ooh. We reckon the sun will leave behind the, yeah, you're right, Rowan, what's called a planetary nebula. It's nothing to do with planets. It's named because William Herschel, who first saw planets through through his telescope, and it looked like a fuzzy disk, a bit like the planets would have looked like through his same telescope. I've put this in because this is a Cat's Eye Nebula, and I just thought it fitted in with our cats this session. By the way, Felicette, she's finally, there was I think it's 2017, there was a guy who started a Kickstarter campaign to get Felicette a statue, a bronze statue created. So there is now a bronze statue of the very first cat in space. Not sure where it is, but I think that's really cool. Okay, I wanted to show some different pictures here. This is Orion, where we've just been. This is the Orion Nebula star-forming region. Okay. This is Betelgeuse, the red star that marks Orion's armpit there. And if we follow Orion's belt upwards, up, we come to a red star called Aldebaran. Okay. This is probably one of the largest single objects you will ever see in your lifetimes. You can go outside when it's finally not cloudy. Have a look at that. If it were in place of the sun, Mercury, Venus, Earth, Mars, and probably the asteroid belt too would all be inside it. It's a star that's coming towards the end of its life. Same with Betelgeuse, absolutely enormous. Betelgeuse is ready to end its life. And when it does so, it will do it in spectacular fashion. It will go supernova. Here, Rowan's point out the Hyades. The Hyades is the star cluster that's around Aldebaran. Aldebaran isn't part of that cluster. It's just in the same part of direction, but the Hyades are. If you look just here, these are some things that I think of as the flies on the bull's back. These are the Pleiades or the Seven Sisters. They're very young stars. They're only a few million years old. It's very young for a star, honest. But if you look somewhere in the horns of Taurus the bull, between the horns, you can see. Oh, Brian's saying Betelgeuse has a radius. This star here is radius out as far as Jupiter. Yeah, do take a look at these things. That sizes are absolutely incredible. But close to the horns of Jupiter, close to the horns of Taurus, we can see this. Now, this was first seen probably around 1054. It was certainly recorded then by Chinese astronomers. This is the remains of an exploded star. This is the Crab Nebula. Yeah, thank you, Rowan. It is M1. That means it's object number 1 in Charles Messier's catalogue of fuzzy objects. That's literally what it was. It was a catalogue of fuzzy objects. Anthony says there's a pulsar at the center of it. There certainly is. And I'll go on to that now. Pretty much the same thing happens here as happened with the Sun. It expands first into a red supergiant and then collapses in and causes enormous explosions that basically just rips the star apart. Chinese astronomers, to them, it would have shone brighter than the full moon. It's probably like a second star when this exploded, and it would have shone like that for a couple of weeks before fading away. There is a star depicted on the Bio Tapestry. Of course, we would have seen it on this side of the world as well. Some say that that is depicting this same supernova event. That was 1066, not too long after the 1054 explosion. And I should think that that would have been a big part of people's lives at that time. The core is really, really interesting. Now, it's quite amazing to think about what stuff is made of. If you touch something that's around you, if I'm just touching the chair that's next to me at the moment, it's wooden, it feels fairly solid, but it's all made of atoms. And atoms are mostly absolutely nothing. They tried experiments where they fired alpha particles, those are just like 2 protons and 2 neutrons, think of them as tennis balls if you like, at gold foil. And most of them just go straight through. Imagine that for a moment. Look at the wall in front of you. Imagine lobbing tennis balls at it and the vast majority of them just going straight through the wall. I've got a mug here. I'll just stop sharing for a moment. I've got a mug. If this were the nucleus of an atom, the edge of the atom is going to be at least 1 kilometer over there, if not more. Atoms generally are 10,000 times the diameter of the nucleus itself. And that distance between the nucleus, where the protons and neutrons are, and the electrons that are orbiting, a bit like they're orbiting planets, only a bit like, it's a useful model to have in your head, are a long, long way away. So what happens when these stars collapse is those electrons get squished into the nucleus. All of that space goes. And you end up with something so dense that if you took a little piece of it about the size of a sugar cube, it would weigh the same, well, very roughly, as all the people on planet Earth put together. Okay, it's about 100 million tons. Absolutely incredible. And if I go back to my screen share now and go back to that slideshow, I'm going to tell you a little bit about an amazing discovery from this woman here. She's now Dame Jocelyn Bell Burnell. Absolutely amazing woman. She started going to school in Northern Ireland. She went to a school where basically they didn't teach science to girls. I think her parents said something about this. I don't know whether anything happened because of it. But her early schooling did not involve much science at all. She actually failed her 11 plus. But her parents got her into a boarding school for Quakers, and she studied and she started developing a love for physics there. She ended up going to Cambridge, and she, in 1967, I believe, she discovered a little, here, I'll show you what she discovered, just here, a blip. She was using radio telescopes. She was looking at information coming through radio waves, and she noticed this. She was a graduate student at the time, and she spent a lot of time trying. She was very thorough, and she's later said that she had very much suffered from imposter syndrome. So she was doing her best not to be kicked out. I don't think there was anything to worry about in reality, but she found this, and she really had to convince her supervisors to take this seriously. There was a little joke that went around the lab. This got a nickname, an LGM1. And LGM sounds really, really sciencey until you translate it into little green men. They had no idea what this little signal was. This, okay, just here is a little interference signal, which looks quite similar. You think you really have to know what you're looking for. But she stuck with this, and this was the very first pulsar that she had discovered. It's called, CP 1919 plus 21. That's just a reference to where to find it in the sky. They did find out that it wasn't from little green men. It was actually from these neutron stars that would actually pulse out radio waves as they spun. There's a little clip that I found of her explaining it by Jodrell Bank, and she said, well, they said, well, how strong were these radio signals? And she gave the example of putting a piece of steak where they were going to detect the signals on the radio telescope, so in the center of the radio telescope. And she said, if that pulsar was where the moon is, you could cook your steak with the signals coming off. Absolutely. Amazing, amazing woman. There was a Nobel Prize that was given out for the discovery of the pulsar. It was the first time an astronomer had ever got the Nobel Prize. Was it given to Jocelyn Bell Burnell? No, it was given to her supervisors. Yep, the ones that she had to convince to look carefully at that. Now, there's another little video. I wanted to try and share it, but there's all sorts of copyright issues when you start looking at the YouTube videos. But I'll try and get the link to you at some point. It's her talking about the time that she was in. It just really brings home the atmosphere that she was in right then. She talked about coming back to the lab in January. This was just after she discovered the pulsar. She was really bouncy and happy because she just got engaged, and she wore her engagement ring to the lab. And she said that was a mistake. It was a mistake because married women didn't work. If a married woman worked, that was because it was thought that was because the man didn't earn enough to support her, and that was really frowned upon. Fortunately, she carried on working. There was an uproar about her not receiving the Nobel Prize. She's won all sorts of other prizes as well. There's a whole list of honors because she's been such a fantastic scientist. I still think it's a shame that she didn't get that Nobel Prize. But in 2018, she got the Special Breakthrough Prize in Fundamental Physics. It's a really, really top-end prize. I think it was about 2.3 million. Maybe 3 million is also a number that's bandied around. Don't take my word for it. But I'm going to go for the £2.3 million prize. She donated it all and more. I think there's been £3 million altogether to help females, minority, refugee students who want to become physics researchers to actually get there. Now, what I want to say about that is part of it is I'm overwhelmed that it was such a lovely thing to do, and it's an amazing story, and it's nice that somebody up there recognizes that it's still tough. But 2018 is going to be looked at in rose-tinted spectacles as, those glorious days before COVID. 2018. Why does anybody need to do that? Surely we should have a situation where that is not necessary, but clearly it is, and we have to really commend her for not only her science, but actually solving some of the problems that are still around in science now. Oh yeah. The next one is just black, because if you get a star even more massive than one that would produce a neutron star, you will end up with a black hole. Okay. If you think about a neutron star, is a little bit like squeezing, I'm just going to brush up, the sun into about a city the size of Derby. Small. Okay. Remember, you could fit 1.3 million Earths in that. A neutron star, sorry, a black hole is like squishing this entire sun into a full stop, except it's even smaller than that. There is some really, really weird stuff that goes on around black holes because the gravity is so great. We can detect them, and that's because of X-rays coming from accretion disks of stuff as it falls down towards the black hole itself. But one last thought I'm going to leave you with. This here. This is a cloud of dust and gas. You will find a nebula like this whenever a star ends its life. And this is exactly where we started. A nebula, a cloud of dust and gas. If it cools enough, then it can come together and form new stars. And because we know that there are planets in the solar system, we're living on one, that's a pretty good indication that they're there. We know that the sun wasn't what we call a first generation star, one of the very first stars in the universe. Those would have been made of mostly hydrogen. Well, clearly there was other stuff that made the rocks and things that we're living on. So the sun was made from other exploded stars. I think one of you, thank you for whoever it was, said that the sun's actually a third generation star. So it's made from the third cycle of star formation. Now, just think about that for a moment, because that means that every atom in your body was once part of a star. And that iron that's coursing around your veins and your blood right now, that could only have been formed in a supernova event. If you think the stars are just out there, light years away, that's true. But you are also made of stardust. It's not that it's just all around you, it is you. And there I will stop and have a look at some questions. I hope you enjoyed that. Isn't science wonderful? Absolutely. I've got 5 questions. Well, let's ask them. Yeah, as Carl Sagan said, we are all made of star stuff. We are indeed. Okay, Carl here, I'll take this on. Do you think it's possible that Earth will suffer the same fate as Venus if we continue to release high amounts of greenhouse gases into the atmosphere? If so, when? No, I don't think it will get that bad. Simply because we are we're further away from the sun. We have a thinner atmosphere already. Our atmosphere, if we go back 4.5 billion years, largely came out of, we had gases coming out of volcanoes. We had lots of carbon dioxide. that way. Do I think that continuing to release greenhouse gases into the atmosphere could make Earth inhospitable to humans? Yeah, quite possibly, quite probably, really. And this is what we need to think about. People often say phrases like "save the planet." Well, to be honest, the planet will be pretty much fine. I can't see anything bar the sun's expansion in 5 billion years' time doing anything to the planet. Do we mean save ourselves as human beings? Yeah, that needs to be done. And the worrying thing is, for me, are the feedback loops. I mentioned the ice being reflective and then the water absorbing more energy. You've also got lots of permafrost in Arctic regions like Siberia, and they're melting and releasing enormous amounts of methane into the atmosphere. Now, I promise cow farts. Methane is the gas that comes out of the backsides of cows. It is incredibly potent as a greenhouse gas. I think it's about 100 times more potent than carbon dioxide. And we're on the cusp of releasing huge quantities of that because of the permafrost melting. People don't tend to talk about that, and I think we need to maybe talk a bit more about it. Hope that helps. Anthony's added to that. There was a particular set of circumstances that promoted the effect on Venus. One thing for a start, a high concentration of carbon dioxide in the atmosphere. Also, Venus has not had plate tectonics, so no way to lock carbon dioxide away in rocks. Yeah, thanks for that, Anthony. Thanks for reminding us once again about the importance of geology. The carbon dioxide can be taken up by sea creatures. They fall to the bottom, it ends up as rocks, and the rocks get subducted down under other rocks and end up deep in the earth. This is one way that carbon dioxide comes out of the atmosphere. I'm just going to invite some astronomers up. Do just ignore the invite if you don't want to come. That's absolutely fine. I could just once again do with a glass of water. And I think some of you might want to answer these things. Anthony says, always trust an astronomer. I'm actually going to try and invite you. Why not? Probably not going to work, but we'll give it a go. Hi, Graham.
Hi, Ducky.
And I think that's everybody. And Anthony says, "Oh, heck." We'll see if he appears. He might appear briefly. He might not. Hi, Chris. How are you?
Hello.
I'm just having a look at these questions. I've got to ask this one. Oumuamua. I can never say this.
Oumuamua.
Thank you. Interstellar rock, alien probe, or galactic pizza delivery service? I think that's got to be the best question yet.
Well, it's definitely an intergalactic rock. It's come from outside of our solar system anyway. And it's off on its way out again.
There you go. I hope that answers that. Unfortunately, no intergalactic pizza for us.
I think it's Hawaiian, isn't it? I think the
name. It sounds Hawaiian.
And I think it means visitor from afar or something like that.
Yeah.
But I don't speak Hawaiian, so I'm not sure.
No, I do know one word in Hawaiian, and that's a'a, which is this kind of really it's a lava flow.
And they're going,
Just imagine to walk on it. It's well known.
Yeah, there's a lower, isn't there? I know that.
I'm going to say something a little bit about this because I think a lot of people will be interested. Phosphine found on Venus initially suggested the possible presence of life. However, now scientists are suggesting that it may be due to geological processes. Are there any ideas as to what geological process could be taking place on Venus to generate phosphine? And then we have an edit. Apologies. It seems that just 2 days ago it was announced that phosphine is no longer thought to be present on Venus.
Oh, right. I didn't know that.
Well, I read something, but it was a bit more than 2 days ago, where they were doubting and rechecking their data. It was a massive surprise because Venus is not an obvious place to even think about life. I don't know whether either of you would like to say something about phosphine.
Well, the problem with phosphine is that it's very short-lived. So if it's in the atmosphere, I don't know how it's generated, other than biologically. So I don't know any other way it could have got up there if it was there at all. But it's very short-lived, so something must have been replenishing it. So, but obviously now they've decided it wasn't there anyway. So.
That's brilliant. I've just seen one from Toby that I really want to put out there. Why isn't the sky totally full of stars? Now, this is some sort of paradox that I forget about the name of. I don't know if either of you can. Olbers paradox. Thank you, Ian. I don't know whether either of you can talk about Olbers paradox at all.
No, I don't know anything.
No.
Okay,
No.
I'll say what little I
That's the
know.
biggest paradox of all, isn't it, really?
I'll say what little I know and see if it helps anybody at all, but it might be worth looking this up. So Olbers paradox is, well, the idea is they think about space as being infinite, and therefore there are an infinite amount of stars. Therefore, if you look far away enough, there's in any direction there should be some starlight, which is all traveling towards us. So then the question comes in, well, if that's the case, the starlight comes from everywhere. Hi,
Am I on?
Anthony.
Yeah, we can see your eyes.
No.
Yeah.
Need to adjust
Hey,
your
oh.
camera.
Can you hear me?
We can hear
Yeah.
you too. Yes. Welcome, Anthony.
Yeah.
So
Can you hear me all right?
question is
Yes.
why
Yeah,
don't we see
finally.
brightness everywhere? Why is it actually dark? Well, there is dust in space. We've seen some of that, so that will absorb some of the light. We've also got the time that it takes for light to travel. Okay, so for example, the light that has just reached us, or maybe even if you go to the cosmic microwave background, which was radiation that was given off in the Big Bang, is a bit complicated because back then everything was much closer together. So we've got something here that was sent to us over here at that time, but in between, the space between the stars, everywhere you go, has
Got bigger.
expanded. This kind of blows my mind a bit because you've got to think of nothing, having more nothingness. But to get some sort of an idea, the old trick of getting a balloon and drawing on some galaxies with a felt tip pen and then blowing it up will give you an example of how the space between separate stars is all expanding. That wasn't the easiest or best of explanations, but I hope it gave something.
You want to say something, Anthony?
As the universe expands even more. Oh, you're all right. Can you hear me?
Yeah.
Hear me all right?
Yeah.
Can you hear me?
Yes, we can hear you.
Oh, good. Right. As the universe expands even further, astronomy may become rather boring because all the other galaxies will have expanded beyond our observable horizon. So there'll be only one galaxy, and that'll be us.
And gradually we'll move away from everything else.
Yeah.
So there'll be no stars in the sky.
Yeah.
So we're living at an optimum time now.
No,
so
it'd be
get
quite
out there
dark.
and get some observing.
Yeah, don't sell your telescope yet.
Yeah.
Come and join the DDAS.
Ian's
Mind
put,
you, with the way it's raining, I think I might put mine on the market.
Ian's put something really nice, which is way better than my budget explanation. He says, I guess it's because a visible universe is not infinite because the universe is expanding. There's a good thought.
Yeah.
It's
you're supposed to be able to see, is it about 3,000 stars if it's a really dark sky? You know, which is nothing really, is it? If you know, I suppose it's more if you went down to the southern hemisphere because you're looking at a different angle into the Milky Way. I think you can see more. But I think in the northern hemisphere, if you look on a dark sky site, you can see about 3,000 stars with the naked eye. That is
brilliant.
But I'm not counting them.
Yeah, that number keeps going around my head as well. This is a nice one. The astronomers. What does Neptune look like through a telescope?
Very small. It's basically unless you've got a really big aperture telescope, something in the region of 12-inch diameter aperture or something like that, or bigger, it's going to look like a blue star. You might be able to see a little colour in it. You might be able to see it blue as opposed to orange or whatever from a star, and it probably just slightly bigger, but not much. There is, if you went on our website, there is a video taken by Peter Branson that's it's got Neptune and Triton orbiting it. So if you go on the website and try and find that, that's good to see.
Brilliant.
He took a video of it and did it over a couple of nights, and you can see the movement of Triton going around Neptune.
Brilliant, thank you for that. There's one more question that I'm going to say. I know astronomers, we've got somewhere else to go to, I think, so we'll probably wrap this up. Can you use Pioneer 11 images of Saturn for tomorrow's presentation? Rowan, if I can find some, yes, I will. Is there anything else you want to say, astronomers, before we say bye for tomorrow?
No, I don't think...
Well, I can't think of anything.
You're finally here.
No, it finally got on.
That's irony, isn't it?
Anti-climax, that is.
But actually, what we were talking about yesterday about nebulas and things like that, was it yesterday we was talking about? Oh, observing. I think it was Chris was on about the telescopes, and somebody asked what nebulas could you see. Next Friday we're having a talk by the director. He's actually the director of the what is it, Anthony? Come on, help me out. I've gone deaf. The yeah.
University of South Wales, isn't it?
Yeah, but it's the
I
dark
can't think
sky.
of his department.
Oh God, come on. Brecon Beacons. He's the director of the
Gordon
Brecon
Beacon.
Beacons Observatory, and he's going to be talking about observing nebulas. So if anybody's interested, drop me an email and I'll send you the link.
Yeah, it is amazing. Just to let you know about this place, it's a little observatory in the Brecon Beacons that was set up to detect asteroids coming towards Earth. The guy who runs the place is just absolutely fantastic. So that's going to be really, really good.
Martin Griffiths.
Yeah.
Martin's very funny with his talks as well. He's very popular with Tarside, and he's actually got relatives in Derby as well. So
yeah, and it's an amazing little place that he set up to do what, you know, a lot of us assumed that the biggies over at ESA and NASA had already set up. They hadn't.
No.
That I think they're linked in with him now, but yeah, it's really lovely. Okay, so we'll see you tomorrow. Tomorrow is Saturn Day, Saturday. This is when I'll look at Saturn, and I will also do a very, very quick visit to Uranus as well, just so that it's not left out. And then I'll hand over to Derby and District Astronomical Society, who are going to really tell us what's happening with infrared astronomy and the James Webb Telescope. I'm really looking forward to that. I'll be able to drink water too. This is a good thing. And finally, on Sunday, we have the amazing Ian Russell, who's very kindly come along and watched us too. He's an award-winning science communicator, and he's going to really get to trying to imagine those enormous distances that are involved in space. Thanks, everybody. Thanks for all your help. Thanks for coming. Do share. Do come along tomorrow too. Oh, thank you, Starber. That's really lovely. Absolutely incredible, everybody. Interesting and informative. Very cool. I'll see you, astronomers. Hope to see you again up here, Anthony, especially. I'll see you tomorrow too, hopefully with fewer technical issues. Goodbye for now.